Welcome to a lesson with Dr. Powell. Let's take a look at now writing down rigorously using inequalities what we were talking about last time. So again, if we have a function, and let's do the same thing. Let's suppose that's 5. The limit as x approaches 5 of f of x, and suppose that it's equal to some value here, like y is equal to 2 or something. Okay, so how would this work? What we say is given a y closeness, so kind of remember that, given a y closeness. Now, how can we get given the y closeness? Well, we can draw it out like this and put an epsilon here and epsilon there to represent that distance. So basically just given epsilon greater than 0, that is the y closeness. So given any y closeness, even not just one, but any, no matter how small it is. So given any y closeness, so this statement that the limit holds is there exists an x closeness. Okay, so we need an x closeness in here, and maybe we'll use we need a term for, let's use a Greek letter delta. So it'd be the distance from here to make that box. Okay, so delta greater than 0. Now, why am I saying greater than 0? That's only because I'm talking about distance, and distance is going to be greater than 0. And it's going to be positive. So there exists some distance, and we're just using delta. It could be anything, but that's just the notation that we use to represent some distance going this way from that point. There exists delta greater than 0. So there exists an x closeness. So the y closeness and the x closeness occurs twice in the statement. One in the condition here. So given epsilon greater than 0, there exists delta, and then we have a such that, and then they occur again. And it's kind of symmetric. Then we're going to have the x condition right here, such that if we are in the x closeness, so what does it mean to be in the x closeness? Well, that means that the distance that x is away from 5, you can write that as an absolute value. That means distance from something. If you subtract and take absolute values, so you can be on either side. You can be over here, here. If you subtract, take opposite value, that'll be distance you are away from here, from this. So in other words, here's 5. And so here's your x value, so x minus 5 opposite value is that distance. And also, if x is over here, same thing, x minus 5 is going to be negative, but take opposite value, it'll be distance. So if that distance is, so if you're in the x closeness, that means the opposite value of x minus 5 is less than delta. Then, in fact, we're even going to put a 0 here, because that's going to allow us to talk about limits. And limits happen sometimes when there's a hole. And so if x were equal to 5, then it would be defined, but we're going to just assume that we're away from 5, but we're very close to 5. Such that if this distance right here is between 0 and delta, these are strict inequalities. So this means we are in the x closeness. So we start with given y closeness, there exists x closeness, such that if we're in it, or if the x values are in it, and then we have something about y closeness. Then we say we're in the y closeness. So then we could, how do we write that? Well, the y value of the function f of x, the distance of that. So if we're right here, the distance of that from the y value of 2 has to be less than epsilon. So we're in the y closeness. So the distance from there minus 2 to 2, that's the distance. The y value is from 2, has to be less than epsilon, and epsilon is that y closeness. So kind of in summary, given a y closeness, there exists x closeness, such that if you're in it, then you're in the y closeness. So see how this is symmetric, y closeness on the ends, x closeness in the middle. At the last part, there are statements about being in. and it's kind of like and such, and here this is kind of like an if then statement. If in x closeness, then in y closeness. And this is also kind of like an if then statement too. If you have a y closeness, then there exists an x closeness. So you basically have two if then statements. You have an if, a then you have another if, and you have another then, and then it starts off with y, it ends with y, and then in here it's an x, then it's an x. These statements, the beginning part, are statements about existence. And the latter part right here are statements not about existence, but being in the closeness. So being inside. So that kind of distinguishes the parts. So the first part is exists. The second part is being inside. You say, so if there exists a y closeness, then there exists, well, and it's not really quite exist. I mean, I guess the y is for any. So it's really an any and exists. Okay, so any. So I guess that makes the difference there. So it's any and then exists. Okay. So for any y closeness, then there exists. So it's kind of like an any exists, I guess. Okay, any exists and then inside. All right, but you still have an if then statement each time, and it's symmetric because y is on the outside, y closeness is on the outside, and x closeness is on the inside, and you have this statement. So, and that is kind of how we can translate a limit statement right here into a statement like this. Thanks for watching.